In this video, we are revisiting section 4.4. Now, I know we covered all the content from the section in our previous video, but it is really worth our time to stay focused here for a little bit and do a few more examples related to each of the concepts. So I'll be walking through all the important results again and doing some new examples to make sure that you have a couple of illustrations of how they all get applied. Now, the important notion that kicks off everything in this chapter is the idea of conditional probability. Conditional probability is the name of the technique that we use when you're trying to calculate the probability of a specific event. Let's call it event B, and you get provided with additional information about some other event. Let's call that event A. For example, I want to know what the probability is that you're reading a Stephen King novel. And then someone tells me, oh, well, they know that you're reading a nonfiction book. Well, I'm not expecting all of you to be overly familiar with all of Stephen King's work, but he wrote 2 nonfiction books to the best of my knowledge, and everything else is fiction. So the moment someone gives you this additional piece of information, oh, the book is nonfiction, well, now it's probably not as likely to be a Stephen King novel. Well, won't be a Stephen King novel. Could be a book by Stephen King, but a novel would be fiction. So we're introducing extra information. And there are 2 ways to approach problems like this. Often, we're dealing with situations where we can list all the outcomes for the experiment, and those outcomes are equally likely. So if you can list all the outcomes and they are all equally likely, then the definition of conditional probability, where this horizontal bar reads as given, so here probability of B given A, is given by counting the number of outcomes that fall into both events A and B and dividing by the number of outcomes that only fall in event A. If you are not able to list out all the outcomes, maybe you have probability information. What you should notice here is this formula looks very similar, except instead of now counting the number of outcomes, if we have the probability that A and B are simultaneously true, and we have the probability of A, we can just take the ratio of those 2 probabilities. So we're able to do this by counting outcomes, but even if we're not able to do that, if we have certain probabilities, we can apply this formula. So let's look at a couple of examples. Let's say I randomly draw a card from a standard deck of 52. And first thing I'm asking is just, what is the probability that it is a face card? Now, what are the face cards? The face cards are Jack, Queen, King. How many face cards are there in a deck? Well, there are 4 Jacks, 4 Queens, 4 Kings, and so there are 12 cards total in the deck. So the probability that I draw a face card, like I can count the number of face cards, 12, and I can divide by the size of the deck, 52, and of course I can go and express this as a decimal, rounded to 4 decimal places as 0.2308. Now, let's stay with this probability, calculating probability of a face card, but I draw a card and someone looks at it, they're not telling me what it is, but they're telling me that the card is not a numbered card less than 6. So they are telling me it's not a 2, 3, 4, or 5. Now, how many cards in the deck are 2s, 3s, 4s, or 5s? 16 cards. And I'm being told it's not one of these 16 cards. So what's the probability of a face card given that the card is not less than 6? Well, our formula says we can go and count the number of cards that are face cards and not less than 6. And we can divide that by the number of cards that are not less than 6. Now, how many cards are face cards and also not less than 6? Well, none of the face cards are less than 6. So there are 12 cards that are face cards and also not less than 6. But how many cards are not less than 6? Well, that would be the 52 minus the 16 cards that are less than 6. So this would be 12 divided by 36, which in fact is 1/3, or to 4 decimal places, 0.3333. So being given this extra piece of information, someone peeking at the card and telling me, oh, well, I'm not going to tell you exactly what it is, but it's not a card less than 6. That immediately gives me additional information, and I can factor that into my probability now. Let's look at another example. TCU does a survey of their students. They find that 47% of TCU students were born in Texas. So probability of a TCU student being born in Texas is 0.47. Also, 52% graduated from high school in Texas. So probability that they graduated from high school in Texas is 0.52. And finally, 33% were born in Texas and graduated from high school in Texas. So born in Texas and graduated from high school in Texas, that is 0.33. And we now want to calculate the probability that a randomly selected TCU student graduated from a Texas high school given that they were born in Texas. So probability that they graduated from high school in Texas given that they were born in Texas. Trying to find that conditional probability. We don't have the information pertaining to the specific numbers of students, but we do have the probabilities, and our formula says if we want a conditional probability, if we have the probability of the overlap where both statements are true, so if we know the probability that a student satisfies both of these conditions, and we can then divide by the probability of whatever it is that we're conditioning on. The conditioning statement is also the one in the denominator. Then we can do this calculations. The probability of the AND statement is 0.33. Probability of being born in Texas is 0.47. And so if I do this calculation and round to 4 decimal places, it's 0.7021. So there's my probability, like very close to 70% chance. If I know someone is born in Texas, or if I know a TCU student was born in Texas, there's about a 70% chance that they also graduated from high school in Texas. Now, the conditional probability rule can be rearranged to give us a result called the multiplication rule. And all I'm doing is rearranging terms. I take this form of the conditional probability rule, multiply both sides by the probability of A, and I solve, therefore, for the probability of A and B. So the multiplication rule is a way to calculate the probability of an AND statement if I have the probability of one of the statements on its own, or one of the events on its own, and I have the conditional probability of the other event conditional on the first. And if I multiply those two numbers, it gives me the probability of the AND statement. Let's see how that works. During July, a randomly selected day is windy with probability 0.3. So let's write down that first piece of information. Probability that it's windy is 0.3. The performance of an archer can be dramatically impacted by windy conditions. When it is not windy, when is one of those keywords that indicates conditioning. So conditional on it not being windy, an archer hits her target with probability 0.999. So probability of hitting her target, given that it is not windy, is 0.999. While when it is windy, there's my conditioning word again, given that it is windy, the probability that she hits her target is only 0.8. What is the probability that it is windy and she hits her target? Probability that it is windy and she hits her target. So I'm trying to find the probability of an AND statement. And what's really helpful is because I've written down all the provided information, I already see, oh, I have conditioning happening here. Maybe I can exploit that conditioning. I have a statement where I'm conditioning on it being windy. And so if I see that, my next question should be, do I also just have the probability of it being windy on its own? Yes. So I can calculate this as the probability of it being windy multiplied by the probability of hitting her target given that it is windy. And this is 0.3 times 0.8, which is 0.24. Now, just to show you here, if you had a different set of information, you could also have tried to calculate it by doing the conditioning differently. You could have said, oh, let's calculate the probability of hitting the target multiplied by the probability of it being windy, given that she hits her target. But note, we have neither of these probabilities. So with the multiplication rule, you can try setting up the conditioning both ways and do that and check which one lines up with the information you have available. This second approach in purple, we definitely do not have information to do it this way, so that's no good. But if you set it up one way and find that you don't have the information, then just flip it around and set it up the other way. So if you try setting it up with conditioning in one way, see you don't have that information, try conditioning on something else. Let's look at another example. Suppose that a manufacturing process requires 3 steps. The first step is successful 98% of the time. The second step is successful 95% of the time, and the third step is successful 99% of the time. Assuming that successes are independent, what is the probability that all 3 steps of the process will be completed successfully? So, independence comes in here. And we did cover that in the previous video, but just to remind you, we have a special form of the multiplication rule when we know we have independence. When we know we have independence, then probabilities of AND statements just become probabilities of the products of the probabilities. So the probability of A and B just becomes the probability of A times the probability of B. And it extends to multiple events. So if you had the probability of A and B and C, it just becomes the product of those 3 probabilities. And that's exactly what we're trying to calculate here, the probability that all 3 steps will be successful. meaning we want the probability that the first step is successful and the second is successful and the third is successful. And by independence, this is just going to be the probability that the first is successful times the probability that the second is successful and times the probability that the third is successful. And we have these individual probabilities. They're 0.98, 0.95, and 0.99. And if I multiply those and round to 4 decimal places, it's 0.9217. And let's look at another variation of this problem. Still dealing with the same process, we still have independence of steps, but now we want to calculate the probability that none of the steps are successful. So we want the probability that the first is not successful and the second is not successful and the third is not successful. But this is still AND statements. And because of independence, I can still change this to multiplication, except now I'm multiplying the probability that the first is not successful and the second is not successful and the third is not successful. Now, where do I get those probabilities? Well, what is the probability that the first is not successful? It'll be 1 minus the probability that the first is successful. And so this will be 1 minus 0.98, which is 0.02. And the same principle applies to the other two steps. So what I have here is a 0.02, and a similar calculation for the second one gives me 0.05, and a similar calculation for the third one gives me 0.01. And if I multiply these, I'm making an exception and not rounding to 4 decimals, because they would just be 0. I'm writing all 5 decimals so that I have a non-zero solution. But there we have it. So we applied 2 things here. We still used multiplication rule with independence, but we also added to that the complement rule for each of the individual steps, flipping their probabilities around from being successful to being not successful. So I applied independence there. This slide just summarizes the definition of independence in terms of conditional probability. Sometimes you can calculate a conditional probability and you will see that it's the same as the unconditional probability. And if that happens, that tells you that you have independence. This is just where the modified version of the multiplication rule comes from. So here's that multiplication rule for 2 events. And let me just repeat it one more time for 3 events. And this can be extended to 4 or 5 or 10 events. As long as they're all independent and you have AND statements, you can convert them to products. Let's do another example of that. A fair coin is tossed 4 times. What is the probability that it lands showing heads? And this should be all 4 times. So no statement is made here about independence, but it is reasonable to assume that consecutive coin tosses are independent. Because if I toss a coin and see heads, that tells me nothing about when I pick up that coin a second time, whether I'm going to see heads or tails. So probability of seeing heads 4 times means I get first coin toss gives me heads, and the second coin toss gives me heads, and the third coin toss gives me heads, and the fourth coin toss gives me heads. And then by independence, I'm just going to multiply these probabilities. And if I have a fair coin, on any coin toss, what is the probability of seeing heads? It'll be 1/2. So this is 1/2 times 1/2 times 1/2 times 1/2, which is 1 in 16, which I can write as a decimal to 4 places, 0.0439. Okay, so I was able to use independence here. Similar problem, fair coin is tossed 4 times. What is the probability that it lands showing tails at least once? Now, whenever you see the keyword at least or at most, ask yourself, what is the opposite of that statement? Or what is the complement of that statement? If I say tails at least once, that could mean tails once, or it could mean tails twice, or it could mean tails 3 times, or it could mean tails 4 times. But what is the complement or the opposite? The opposite of seeing tails at least once would be seeing tails 0 times, which is the same as what? Seeing heads 4 times. So, probability of seeing tails at least once is the same as 1 minus the probability of seeing tails 0 times, just applying the complement rule. But that is the same as the probability of seeing heads 4 times. If tails comes up 0 times, it means every coin toss was heads. And we already calculated this probability. It was 0.0439. And so this is 0.9561. Okay, I have one more example here, and this one has quite a bit to it. So it's worth paying close attention here, and I'll definitely do one more example like this in class as well. One of the standard tests for HIV is called the Elias test. Assume this test returns a positive result for 99.8% of those with the HIV virus. 4 is a keyword here. 4 is the same as given. So this tells us you get a positive test result given that you have HIV, 0.998. And that seems good, right? You want this test to actually come back positive if someone is HIV positive. So it looks like a good test. Next, when the test is given to someone not infected, and when is another one of those keywords, conditioning. If you see 4, if you see when, if you see the word given itself, it tells you there's conditioning happening. So here it says, when someone does not have HIV, that's what we're now conditioning on. The probability of a positive test result is 1.5%. And just take a note here, this first number is an example of a true positive. If someone has the disease, we want the test to come back positive. The second one is an example of a false positive. Like if you are not HIV positive, you don't want a positive test result back. So we'll discuss that again a bit more during our Zoom time. Final number we get here, if we restrict our attention to heterosexual persons in the US, without specific risk factors, then their infection rate is about 0.02%. So what is the probability that a randomly selected heterosexual person in the US is HIV positive? It's 0.02%, which is 0.0002. We now want to calculate, just in general, if I randomly select a person, what the probability that a randomly selected person will test positive. So let's unpack how we can get to the probability of someone just having a positive test. We already know we're looking at a population with two pieces to it: people who are HIV positive and people who are HIV negative. So if we look at the positive group, it has two parts: people who are positive and they have HIV, or they're HIV positive, and people who get positive test results and they're not HIV positive. And these two events are mutually exclusive, which means we can just sum their probabilities together. So the probability of a positive test result is equal to the probability of having a positive test result and being HIV positive, and the probability of having a positive test result and not being HIV positive. And for each of these now, we have conditional information, in one case conditioning on HIV, in one case conditioning on not HIV, that'll allow us to apply the multiplication rule. So the positive and HIV positive, by applying the multiplication rule, we can calculate the probability of being positive given that you're HIV positive, and multiply by the probability of being HIV positive, and add to that the probability of a positive test result given that you're not HIV positive, and multiply that by the probability of not being HIV positive. Now we can just plug in some numbers here. Probability of being positive given that you're HIV positive, we wrote down, was 0.998. And the probability of being HIV positive, we know, is 0.0002. Next, we're looking at the false positives. So given that you do not have HIV, the probability of a positive test result, that's only 0.015. And what's the probability of not being HIV positive? Well, this is clearly the complement of being HIV positive. So it would be 1 minus the 0.0002, which will give us 0.9998. And if I do these individual components of the calculation, it gives me an answer rounded to 4 decimals of 0.0152. So if I just randomly select a heterosexual person in the US with no additional risk factors, the probability that that person tests positive for HIV is about 1.5%. Let's stick with this example for a couple more minutes. So exact same setup, except what I'm trying to calculate now is if, or given that a person has a positive test, what is the probability that they are in fact infected with HIV? So I want to know, what is the probability of having HIV given that you have a positive test come back? It's worth noting here that the conditioning is flipped around from what we had previously. If I scroll up a little, we were conditioning on someone being HIV positive or not being HIV positive. Now we're trying to condition on the test result coming back positive. So not actually disease status or on looking at presence of the disease, But we have a definition for conditional probability, right? We can calculate it as the probability of being HIV positive and getting a positive test result, and divide that by the probability of a positive test result. And this last number we just calculated in the previous example, 0.0152 to 4 decimals. So probability of being HIV positive and having a positive test come back, well, we calculated that as well, but the way we did that was by conditioning on being HIV positive and multiplying by the probability of being HIV positive. And so I could just have lifted this from the previous example, but what you should notice here is I applied the definition of conditioning, right? And then I applied the multiplication rule in the other direction. So this is just the definition of conditional probability. And secondly here, it's the multiplication rule, but I'm conditioning in the other direction. These two things together, they're sometimes known as Bayes' theorem. We're not going to delve into that too much, but if you wanted to know what it is that we're actually doing here, it's called Bayes' theorem, because it's allowed us to flip the conditioning around. Here we were conditioning on a positive test result, and now suddenly we find ourselves conditioning on someone being HIV positive. And the reason this is just such a useful result is it allows us to restate the problem in terms of quantities that we know. We know the probability of a positive test result given that you are HIV positive is 0.998. Probability of being HIV positive is 0.0002. And we had calculated the probability of a random test being positive is 0.0152. And so if we do this division, we get rounded to 4 decimals, 0.0130. So just unpack this for a moment. This says, if we randomly select someone in the US, a randomly selected heterosexual person with no other risk factors, randomly select that person, test them for HIV, the test comes back positive, then the probability of them actually being HIV positive is only 1.3%. Suddenly it looks like the test is not that good, because what's going on? Because the test had a true positive rate of 99.8% and a false positive rate of 1.5%. Those are really good numbers for a test. The problem is just that if you are looking at the general population, even though this false positive rate is low, there are so many people in the population that are HIV negative that would have false positive results, that if we're just looking at people in general, you are a lot more likely, if you're just randomly selecting a person, to select someone who is HIV negative and gets a positive result than actually select someone who is HIV positive and get a positive result. And that has everything to do with how rare HIV positive status is, at least in this target population. So does that mean we shouldn't trust these tests? No. Usually, a doctor is not just going to randomly test someone for HIV. There are usually other risk factors, and that has the effect of adding layers to the conditioning. Like one factor could be drug use, if someone shares needles. So if someone goes to the doctor and says, well, I don't know what happened, but I was in this risky behavior. I think I may have been exposed to HIV. then that is already an extra layer of conditioning, which means they're in a smaller subset of the population now where HIV positive status may be more likely. But what you'll see is we'll look at this false positive and true positive rate information again, specifically in the context of COVID-19. But that is the end of this video, and I will see all of you online on Zoom.